Before we look at the next example in section 4.1, we want to kind of make a comment and highlight some of the key elements of theorem 4.11. Recall that we get the existence and uniqueness of the initial value problem, or the differential equation, provided that those coefficient functions are continuous, and also that the leading coefficient function, the one that goes with the highest order derivative, should be non-zero for every value of x in the interval I. We need both of those conditions, continuity and non-zeroness of the lead coefficient, in order to guarantee the existence and uniqueness of our differential equation. Specifically, if the lead coefficient a(n) of x is not equal to 0 for some x in the interval, then the solution of a linear initial value problem may not be unique or even exist. Okay. And actually this is a typo. It should say if the solution is equal to 0. For example, if we look at this differential equation, okay, the leading coefficient, so the a sub n here, this is a second order differential equation. The leading coefficient is x squared, and we see precisely that x squared is equal to 0 when x equals to 0. Okay? So essentially what that means is that this theorem does not apply. We're not able to guarantee by using this theorem that this differential equation has a solution, or furthermore, whether or not, if there is a solution, whether or not it would be unique. In this case, it actually turns out that there is a solution, and I'll let it up to all of you to verify this, but one of the things that you would see is that the function y equals cx squared plus x plus 3, it is indeed going to be a solution to this initial value problem. So we do have a solution, however, we do not have uniqueness, because for any choice of the parameter c, we would have a solution to this differential equation. Okay. The next thing we're going to look at is boundary value problems. So we're going to want to solve our differential equation. Let's look at a second order one. So we have a2 of x times the second derivative of y with respect to x, plus a1x times the first derivative of y with respect to x, plus a0x times y is equal to some function g of x. And what makes this a boundary value problem as opposed to an initial value problem, if we go back, in an initial value problem, all of the preliminary conditions are at a particular point. Usually it's almost always exclusively the independent variable equals to 0. But with a boundary value problem, what we can have happen is that the value of the function could be specified at two different points. So we want the function y to have the value y sub 0 at a, and we want the function y to have the value y1 at b. And that's what we call a boundary value problem, which we'll typically abbreviate BVP. These subject to our constraints, these are what we call the boundary conditions. A solution of this problem is a function that satisfies the differential equation, so it has to satisfy this differential equation, and the function has to have the prescribed boundary values. In other words, its graph would pass through the points a, comma, y0, and also pass through the point b, comma, y1. In examples 3, we're going to see that for a boundary value problem, a lot more different types of behaviors can occur. A boundary value problem can have one, infinitely many, or perhaps even no solution. Excuse me. Let's take a look at example 3. Here we have the differential equation x double prime plus 16x equals to 0, and we're thinking of x as being our dependent variable, and we're thinking of x as being a function of t in this case. The textbook tells us that a solution to the general differential equation is going to be x equals c1 cosine of 4t plus c2 sine 4t. Let's actually go ahead and verify this. Let's check this. So starting with the function x, we're going to need the second derivative. So we're going to begin with the first derivative. The derivative of c1 cosine of 4t, from the chain rule, that's going to end up being a negative 4 c1 sine 4t. The derivative of c2 sine 4t, again chain rule, that's going to be 4 c2 cosine 4t. That's our first derivative. Let's now go ahead and take the second derivative. this will give us a negative 16 c1 cosine 4t, and then this will give us a minus 16 c2 sine 4t. So that's our second derivative. Let's verify that this satisfies the ODE. Again, it was x double prime plus 16x equal to 0. So we're going to take our second derivative. This is negative 16 c1 cosine of 4t minus 16 c2 sine of 4t. We're going to add to it 16 times x, that's c1 cosine 4t plus c2 sine 4t. We want to check, does that equal to 0? Well, sure enough, if you distribute the 16 into the first term, that'll give us a 16 c1 cosine of 4t and a negative 16 c1 cosine 4t. So those two terms will end up canceling. When we distribute the 16 into the second term, you get a 16 c2 sine 4t, and that will cancel with a negative 16 sine 4t times c2. So we do get 0 equal to 0. So indeed, this function is a solution to the general differential equation. What we now want to look at is to see if we can come up with a solution to the following boundary value problems. And in part A, we're going to continue to work with this differential equation. So we have x double prime plus 16x equal to 0. And we want to solve this subject to the boundary values. X of 0 should be equal to 0, and x of pi over 2 should be equal to 0. So let's first begin by plugging 0 into the function. X of 0, this is going to be c1 times the cosine of 4 times 0 is 0, plus c2 sine of 4 times 0 is 0, and we're told that this should be equal to 0. Well, the cosine of 0 is 1. The sine of 0 is 0. And so this would tell us that c1 is going to be equal to 0, because this term will disappear. So if c1 is 0, then we know at the moment that if we plug that in, c1 times cosine of 4t is going to be 0 times cosine of 4t. So the first term disappears. We have x equals c2 sine of 4t. This is our x of t. And now let's plug in our second boundary value. We want x of pi over 2 to be equal to c2 times the sine of 4 times pi over 2. And this should have the value of 0. That tells us that c2 times the sine of 2 pi equals 0. Well, the sine of 2 pi is 0. And so we end up getting 0 equals to 0. But what does this mean? Well, essentially, if you look at this condition right here, what this tells us is that this boundary value, no matter what value of c2 we pick, this will always be a true statement, because at that boundary value, the sine of 4t term is going to be 0, which means that no matter what you pick for c2, multiplying it by 0 will always give us 0. So what that means is we're actually going to have infinitely many solutions. The function x of t equals c2 times the sine of 4t for any real value c2 is a solution. So you pick a real number for c2, you plug it in, that would give us a concrete function. For example, if c2 is 3, then we would see that the function 3 sine 4t would solve the boundary value problem. If you pick c2 equals to negative 5, then the function negative 5 sine of 4t would solve the boundary value problem. So this differential equation with these boundary values would have infinitely many solutions, and the infinitely many solutions we get are the functions of this form. Let's take a look at part B. So we're working with the same differential equation. Let's consider new boundary values. So from above we have our ODE, and this time we want the boundary values x of 0 is going to be equal to 0, and x of pi over 8 is going to be equal to 0. In all of these, all of the x of 0s are equal to 0, so I should have just kind of left it there. But when you plug 0 into this function, we saw that the implication for this, we get out 0, we know that this is going to imply that C1 equals to 0. So we already know that the function is going to be of the form x of t equals C2 sine of 4t. Now let's look at the second boundary value. If I plug x of pi over 8 in, this is going to be C2 times the sine of 4 times pi over 8, and this is supposed to be equal to 0. This gives us C2 times the sine of 4 pi over 8 reduces to the sine of pi over 2, and then the sine of pi over 2 is 1, so this would tell us that C2 equals to 0, which means that this time we just get the constant function x of t equals to 0. We plug in those functions, C1 is 0, C2 is 0, so in this case we get a single solution. So maybe I shouldn't say unique, but we get one solution. Let's see what happens in part C. So in part C we're going to change it. We're still keeping x of 0 equal to 0, but now we have a new boundary value. We want x of pi over 2 to be equal to 1. And keep in mind what makes the boundary value problem is the fact that we're giving values of the initial function at different points. We've seen twice previously how x of 0 produces C1 equals to 0. Now let's evaluate it at this new boundary value. We need x of pi over 2 to be equal to 1. Well, x of pi over 2, right now we know we're working with x of t equals C2, the sine of 4t. So it's going to be C2 times the sine of 4 times pi over 2 should be equal to 1. This is going to be C2 times the sine of 2 pi equals to 1. But the sine of 2 pi is 0. And what we end up with is a contradiction. We get that 0 equals to 1. So not only is this a contradiction, but what this tells us is that this is not going to be true for any value of C2. So no matter what value of C2 we pick, this will always reduce itself to a contradiction, which means that there is no solution. And it's very important under this setup to understand what we mean by no solution. The function x, we already know, the function x with the C1 and the C2, that is a solution to the general ODE. So it's a general solution. When you talk about the boundary value problem, that's the ODE coupled with these boundary value conditions. And that problem, to find a function that satisfies this ODE and also satisfies these bounds, would be impossible. So we say there's no solution, and it's no solution to the boundary value problem. The next thing we're going to look at in this section is homogeneous equations. Let's suppose that we have our nth order linear differential equation. So in standard form, we know what it looks like. This is of degree n. We have our coefficient functions ai of x, and then usually we have it kind of set equal to a function of x. And so if it's set equal to 0 in this case, we say that it is going to be homogeneous. So a differential equation where you have all of your y terms on one side and we have 0 for the function of x on the other side, it's said to be a homogeneous differential equation. On the other hand, if we have our classical general example where we have some function of x on the right hand side, then we say that it is non-homogeneous. So homogeneity in this context is just a matter of looking at what the g of x function is on the right hand side. If it's 0, that makes it homogeneous. If it's a non-zero function, then it is non-homogeneous. Okay. As an example, if we look at this function here, 2y double prime plus 3y prime minus 5y equals 0, this is homogeneous, it's linear, and it's a second order ODE. This one here, we have x cubed times y triple prime plus 6y prime plus 10y equals e to the x. This one would be third order because we have a third derivative. It's linear in the variable y, so it's linear, but it would be non-homogeneous because on the right hand side we have a function of x that is not identically 0. We will see that to solve a non-homogeneous linear equation, we will first start by actually solving the associated homogeneous equation. So this example, the function given under label 7, this is the more general situation that we have. So this is the more general situation. And to solve this one, we're actually going to revert back and first begin by solving the associated homogeneous equation, where we set g of x equal to 0, and first solve this simpler one. One of the things that you might have seen in Calculus 1 when you're going through the different notations for a derivative, the most common ones are like your prime notation, f prime of x, y prime. We've also seen the Leibniz notation, the dy dx, which is very helpful, especially when you do things like related rates. But a notation in that class that sometimes gets overlooked and maybe not used as much is the differential operator notation for the derivative. Okay. So if we use the capital letter D, this is going to be our differential operator, which is essentially, we're thinking of it as dy dx. It's also sometimes written as dy, which is the derivative with respect to y. For example, if we apply the differential operator d to the function of cosine of 4x, you're just simply differentiating this. Cosine of 4x, using the chain rule, its derivative is negative 4 sine 4x. If you apply the differential operator d to 5x cubed minus 6x squared, its derivative would be 15x squared minus 12x. And then if you want to do higher order derivatives, you just have like a power of d. So d squared would be the linear application of the differential operator d twice. So this is our classical second derivative, d squared y dx squared. And similarly, if you want to look at the differential operator notation for the nth derivative, it would be dn of y. We can actually apply differential operators and kind of think of them as in polynomial style, where a polynomial expression involving d would be something like d plus 3, d squared plus 3d minus 4. We could have 5x cubed d cubed minus 6x squared d squared plus 4xd plus 9 are also differential operators. Okay. In general, we define the nth order differential operator, which is how I'm going to describe it. Sometimes people also call it a polynomial operator, but it's of the form an of x d plus an1x of dn1 plus all the way down until we get to a1 of x d, that'd be the first derivative, plus a sub 0 of x. And then what we're going to do is we're going to think of these operators as applying to functions. So let me just kind of focus on this one here. What does d plus 3 do? So let's suppose we have a function y of x. And let's suppose that I have the polynomial differential operator d plus 3. So this is an operator, the differential operator, and this is a function of y. What we can do is we can take the differential operator and apply it to the function. And I'll explicitly show the dependence on x here. But what this would do is it's kind of distributive. This would be the derivative of y plus the derivative, plus 3 times y of x. And so essentially what we would get y prime of x plus 3 y of x. And ultimately what this is going to do is allow us to kind of take and rewrite our differential equations as our function, our solution function, with some differential operator being applied to it. Okay. These types of differential operators are very, very nice. They're linear in particular. What that means is that you can pull constants out. So if you had the differential operator of applied to a constant times a function, this is simply going to be the constant times the differential operator applied to the function. They're also linear. If you want to take the differential operator d and apply it to the sum of the two functions f plus g, this is simply a matter of applying the differential operator to d and to f and then adding the results. So it's technically linear. Some people like to think of it as like a distribution kind of thing. There's no harm in thinking of it like that. And then more generally, if you have, let's suppose, some constants alpha and beta, applying our rules from above, this is simply going to be the constant alpha times L of f of x plus some constant beta times L of g of x. This is what it means for a operator to be linear. So if you have an operator that satisfies condition 9, we refer to it as a linear operator. So for example, let's take a look at, I know that the book shows this, but let me kind of do this by hand together. So in this operator notation, let's look at the following differential equation. So let's suppose we start with y double prime plus 5y prime plus 6y, and let's suppose that this is equal to 5x minus 3. What we would like to do is kind of write the left-hand side in differential operator notation. So one thing we know is that we have this one here is the second derivative. So you can think of this as the second derivative applied to the function y, plus this is the first derivative, 5 times the first derivative applied to the function y, and then we have just simply plus 6 times the function of y equals 5x minus 3. If, in essence, you can think of it almost as if you're factoring the y out, but really what it is it's the application of this particular differential operator. We're taking the second derivative of y, we're then adding 5 times the first derivative, that's 5 times d applied to y, and then we're adding 6 times the function, that's just simply 6 times y, is equal to 5x minus 3. And so, in essence, that linear differential operator we're thinking of in this case, you can think of the left-hand side as being the differential operator d squared plus 5d plus 6 applied to the function y. And compactly, I didn't write it like this, but I can take one more step. But if you call this L, then this differential equation will be written as L of y equals 5x minus 3. This brings us to the superposition principle. And what this says is that if we have the sum of two or more solutions of a homogeneous linear differential equation, will also be a solution. Okay. So let's suppose, in addition to having, let's say, two solutions, because of the linearity of the differential operator, let's suppose we have k solutions to our homogeneous nth order linear differential operator. Let's call them y1, y2, all the way up to yk. If these are solutions of the homogeneous nth order differential operator on the interval I, then their linear combination, which is formed by just taking constants times each of the solution functions, where ci from I equals 1 to k are just constants, then that will also be a solution on the interval. Okay. So be careful, this applies to homogeneous equations, not non-homogeneous equations. If you wanted to kind of see a sketch of this, you can look at it. It's in the notes. I'm not going to do much with this. But a couple corollaries of this. So a constant multiple of a solution will also be a solution. So if you have a solution, let's call it y1 of x, then multiplying it by a constant will also produce a solution. And for a homogeneous linear differential equation, they will always at least possess one solution, namely the trivial solution y equals to 0 will always work.